All right, so there's one piece of a reaction that we have not talked about yet, and we're going to talk about in this chapter. So energy is one of the products or reactants that we have yet to discuss. So depending on whether the reaction is exothermic or endothermic will determine whether energy is a product or reactant. So the studying energy in chemistry is going to fall under thermochemistry. So thermo means heat, chemistry means chemistry. So the heat or energy in chemistry. The topics that we will cover in this chapter. So these are on the front page of the packet that we passed out on the last day we were together. They're the learning objectives. I kind of briefly simplified them. If you weren't there on the last day, the packet will be posted in the Google Classroom for you to be able to access. Some of the topics, so we'll have energy units and conversions, so that will be in this video. We'll learn about the joule and the calorie. We'll also in this video learn about the difference between heat and temperature. We will also look at in the future exothermic and endothermic reactions, so whether heat is released or absorbed. We will also look at curves that are associated. So we'll look at exothermic and endothermic curves related to reactions. We'll also talk about calorimetry. So in this case, the amount of energy that is, say, absorbed by a system would then be released by the surroundings. So we'll explore that idea. We'll also look at the phase change heat transfer for water. We'll revisit the heating curve for water. So if you remember, we had kinetic energy on the slope parts, and during the phase change, we had a change in potential energy. So we'll talk about the heat transfer when that potential energy is either increasing or decreasing during that phase change. Also, our good friend, stoichiometry, comes back with heat. We'll talk about heat cell formation. So how much heat is required to form products, how much heat is required to form reactants, and we'll have a equation for that. We'll talk about bond energies. So with bond energies, going back to Lewis structures, it will be important. We'll look at the bonds that are within compounds. In order to break a bond in the reactants, we're going to have to add energy. And then in order to form bonds in our products, energy will then be released. So we'll explore that. And we'll also explore Hess's law. So reactions can be broken down into steps in order to calculate heat indirectly. So we'll look at, that'll be the last thing we'll talk about. So this is on page 2 of your guys' chapter packet. We'll talk about energy. It's the capacity to do work or to produce heat. So it's anything that is not matter and can cause a change in a chemical reaction, such as energy, all right? So it's either going to be a reactant or a product, and we'll discuss that in the future. So we have two types of energy that we're going to concern ourselves with. They're going to be potential and then also kinetic energy. Now we're going to talk about how heat is measured. So we'll talk about the calorie and the joule. So the calorie is the amount of energy it takes to raise the temperature of 1 gram of water 1 degree Celsius. So we can either have the little c calorie or the big C calorie. So the little c calorie is going to be a smaller unit, where the big C calorie is going to be a larger unit. We'll have the conversion here in a second. It's going to be very similar to, say, the conversion between a gram and a kilogram. The big C calorie is actually the one that is calculated for food. So it's on the back of your food label. The big C calorie is in food. So the joule. So the joule is the SI unit for energy. Your B in joules or kilojoules. Some examples is the energy needed to lift a small apple 1 meter against gravity. The energy in 1 heartbeat. And then there's also 1,000 joules of energy in a match. So when you were lighting your Bunsen burner throughout the year, there's about 1,000 joules of energy in that match that you guys used. Now here's the conversions. So we can convert between a calorie and a joule. So 1 calorie equals 4.186 joules. And then 1 big C calorie equals 1,000 little c calories. So very similar to if you were to go from, like, say, kilogram to gram, where there's 1 kilogram to 1,000 grams. Very similar here with the big C and little c calorie. And here is James Prescott Joule. He is where the unit joule comes from. All right, here's the scientist. So here's some sample calculations. So in this first one, we're going to convert 782 joules into calorie. So this is where I would recommend stopping or pausing the video and calculating this for yourself. I will show the calculation here in a second. But I would recommend stopping the video and calculating this yourself using the conversions that were on the previous slide. So here is the setup that I would use. Again, I want my units to cancel. So I'm going to have 782 joules. And then if you notice, I have joules on the bottom. So 4.186 joules to 1 calorie equals 187 calories, right? When you think about significant figures, 782 joules has 3. So my answer should have 187 calories. Our next calculation is going to be going from then calories to joules. So you have 2,000 calories to joules. So I'd recommend pausing the video now and trying yourself to convert. So here is the setup, 2,000 calories. Remember, you want calories on the bottom now so that the units cancel. Is then going to be, so 2,000 calories are going to end up being multiplied by 4.186 to get 8,372 joules. Again, 2,000 calories has 4 significant figures there. And so our answer is going to have 4 significant figures. Our next example is going to be going from calories to kilojoules. So again, I would recommend pausing the video here and seeing if you can calculate yourself. Here is the setup. So we start with 650 calories. We're going to have one additional step here. We don't have any way to go directly from calories to kilojoules. So we have to go from calories to joules first. Remember, you want your calorie unit on the bottom so that it cancels. When we're in the middle step there, we're in our units of joules. Once we're in units of joules, we're going to convert between joules and kilojoules. So there's 1,000 joules and 1 kilojoule. With the setup, we should end up with 2.7 kilojoules. And then our fourth example, again, I'd recommend pausing the video. We're going to be going from big C to little c. So I'd recommend pausing the video right now before I do display the setup. So from going from big C to little c, we have to remember that there's 1 calorie for 1,000 little c calories. Remember, we want our units of big C calorie on the bottom and our conversion here so that they cancel in order to get little c calorie. And so you should get 90 little c calorie. Next thing we'll talk about is heat. So another word for heat in chemistry is enthalpy. Some symbols are delta H or Q. Those will be symbols that we will use in this chapter. So again, enthalpy is the chemistry wording for heat. Heat or enthalpy is the energy transferred from one object to another because of a difference in temperature. So heat will flow from, or energy will flow from a hotter object to then a colder object. Now the difference between temperature. So temperature is a measure of random motions of particles in a substance related to kinetic energy. So it's related to the movement of the particles, whereas energy or heat is related to the transfer of energy from one object to another. Right? We'll also find out that energy or transfer when related to heat is going to be related to mass, whereas temperature is not going to be related to mass. So how is heat flow measured? So we're going to have a formula here. So we're going to have Q equals MC delta T. So energy equals mass times specific heat, which I will define, and then times the change in temperature. So Q is equal to energy. It's going to be measured in joules. Mass stands for M, so we're measured in grams. And then specific heat is going to be C, and its units are joules over grams times degrees Celsius. You will have a constants table, so different substances will have different specific heats. And this table will be provided to you, and I will have it on the next slide. Specific heat is defined as the amount of heat required to raise 1 gram of substance by 1 degree Celsius. So very similar to the calorie. The calorie is for water, 1 gram of water being raised 1 degree Celsius. Specific heat is then the general term for any substance. It's the amount of heat required to raise 1 gram of a substance by 1 degree Celsius. Then our final variable is the change in temperature. In order to find that, you take the final temperature minus the initial temperature. And again, this is in degrees Celsius. Here's our specific heat table. If you look, water has a very high value. So it's 4.186 joules per gram times degrees Celsius. That it takes a lot of energy in order to raise the temperature of water. Now, if we look down here at the bottom right, when we look at the metals, so you have copper, silver, mercury, gold, lead, very low specific heats. That means it doesn't take as much energy in order to raise the temperature of copper and silver and mercury. So the temperature is going to dramatically go up quickly, whereas with water, you're going to have to add a lot of energy in order for it to raise its temperature. You can also think of a plastic spoon and a silver spoon when you were to eat soup. That silver spoon warms up very quickly, whereas the plastic spoon does not warm up that quickly. So the plastic spoon would have a much higher specific heat, whereas that silver spoon would have a much lower specific heat. That's why it warms up much quicker. The final thing I want to look at here is if we have a kind of a situation to explore what the equation kind of tells us. So if we have a glass of water at 25 degrees Celsius, would a copper penny at 100 degrees Celsius or a block of copper at 100 degrees Celsius warm the water more? So here we have to think about our variable in the equation. So these have different masses. So a copper penny and a block of copper would have different masses. So when we think of Q equals mc delta T, we're thinking about mass here. And again, remember, energy, heat is defined as the energy being transferred from a warm object to a cooler object. And so with the block of copper, since it's larger, has more mass than the copper penny, we would imagine that we would have more heat transferred from the copper block to the water than the penny to the water. So we would imagine that the water with the copper block would then warm up more based on our equation of Q equals mc delta